Hey guys, this is an intro to limits video. This might seem kind of weird because you haven't seen it before, but you'll get more and more used to it as we continue to do questions. Okay, so I kind of brought about the concept of a limit in the previous videos when we were looking at instantaneous rate of change and looking to make that interval between the 2 points as small as possible. So another, this Greek mathematician, Archimedes, he developed this proof for a formula of the area of a circle known as the method of exhaustion. And how it started out was like a limit. So he looked at a circle and found you could approximate the area of a circle by inscribing a square inside and finding the area of that square. And it was similar to the area of a circle. Well, he found that adding more and more sides to that polygon made the area of a circle formula closer to that. Made the area closer and closer to that of a circle. So if I add on a side and make it like a pentagon or a hexagon or an octagon even, like the more and more sides I add to it, sorry, I don't even know, I'm not even counting how many sides, but you know what I mean. The more and more sides you add to that polygon, the closer and closer it is to the area of a circle. Until you, once you get to an infinite number of sides. Okay, that's getting rough. So the area of that polygon is approaching its limit, so the area of the circle, without ever becoming an actual circle. So this is like a concept of a limit. So you're increasing the number of sides. Okay, so another kind of just similar thing to a limit would be like asymptotes. So say you took exponential decay and you looked, and obviously it's getting less and less and less. Let's say we even looked at half-life, and at this thing we do in grade 11, like the radioactive isotopes, we're getting half their mass every 100 years or whatever. We're never going to actually eliminate the substance, but we're going to get it so small that it's almost like zero. So that line continues to get closer and closer and closer and closer and closer and closer and closer to zero until it's like it's almost there, but it's never there. That's like a limit. So we're just looking at what are things approaching. Okay, so I'm going to get into it here. So there's limits. So there's things called left-hand limits and right-hand limits. So depending on, let's say we looked at a graph, we could approach things from the left or the right-hand side. So the thing we're always approaching is in the x-axis. That's what we're always approaching, and we're looking for the y value. Okay, so let's just say we were going to approach something from the left-hand side. So if we wanted to say, what is the limit of this function as we approach 5? We could write that as the limit as x approaches 5 from the left. So from the left is denoted with a minus sign because you're approaching from a smaller value. So let's say we were over here at -2. That's to the left of 5. So over here at -2 on our graph, which is up here, and I'm approaching 5. What's happening? My y values are decreasing, and when I get to 5, I am right at a y value of 2. So, so we could say that the limit of this graph as we approach 5 from the left is 2. So that's a left-hand limit. So if we look at the right-hand side, in another color, let's go green. So let's say we want to look at the limit as x approaches 5 from the right-hand side of the graph this time. So now we're using values that are bigger than 5. So we're on the x-axis. Say we're starting over here at 8, 6, 7, 8, or 9, whatever that is. And we're approaching now from the right and heading towards 5. Looks like we're going to actually get to the same value. So the limit as x approaches 5 from the right of f of x is also going to be equal to 5. So you can see the limit as we approach from either side of the function is actually going to be the same. Sorry, I'm semi-distracted. Okay, back in the game, hopefully. Okay, so anyways, that's a left hand and a right hand limit, we call it. So it's just, we're looking at the x values and we're seeing what y value do they approach. So just to sum up that again, we're looking at what is this x value, what is the y value as we approach a certain x value. So we picked 5. So we're trying to figure out what is this y value as we approach from the left and the right of the graph. Okay, so that's the concept of a limit. So you can have a left-hand limit and a right-hand limit, and they can be the same thing. Oh my God, guys, I wish we were in class because someone would have called me out. That equals 2. Ugh, sorry, I wish I'd never made a mistake. That'd be cool. Would it? Okay, anyways. So you can see that the limit as we approach from the left or right is going to be 2. So it's the same. Neat. It doesn't always have to be the same though. Check this guy out. So if we approached this guy from the left, so let's write, what if we want to do the limit as x approaches 4 from the left of this function, f of x, I don't know what it is, just made it up. So we're over on the left and we're approaching 4, boom, we hit it. Looks like it's at 1. So the limit as we approach 4 of f of x is 1. Okay, cool. Let's see what happens when we approach from the right. So the limit as we approach 4 from the right of f of x is equal to, so we start on the right-hand side. So this is the right, this is the left. So we approach 4 from the right, and it looks like we're stuck here. That's the value we're approaching, -2. So I just made that an open circle because I still wanted this to be a function, and you can only have one y value for every x value, so I just made it an open circle. So it doesn't actually get to -2, but that's what it's approaching. So here's an example of where the limit, the left and the right-hand limit are different. So this left-hand limit is 1, and this right-hand limit is -2. So they approach from the left and right, but they approach different values. So these actually are two different kinds of functions. We would call this guy a continuous function because it keeps going forever. Like you could draw this function without picking up your pencil, right? Like I just draw that. I never had to pick up my pencil. And we would call this one not continuous or discontinuous. Because in order to draw it, I'd have to pick up my pencil here and now start drawing again. So there are two types of functions, continuous and discontinuous or not continuous functions. And we're going to have to be able to tell, are they continuous or not continuous, and we're going to have to prove it. We're also going to have to be able to find limits from the left and the right-hand side and compare them. So that's a requirement in this first topic here, A1. Okay, so we're going to define some rules. So I would definitely write these rules down. Like I would write everything down from these videos personally, but that's me. Okay, so we have a set of rules to follow if a limit, we say if a limit exists. So the only way that a limit can actually exist, so a limit, not a left or a right-hand limit, but just a straight up limit, the only way for a limit to exist as x approaches some number, I just said a, but it could be as x approaches 1, the limit of f of x exists if it meets these 3 criteria. And they're very simple. The 3 criteria that you have to meet are, there has to be a left-hand limit. So like there has to be one, it actually exists. There has to be a right-hand limit that exists. And those 2 limits have to be equal to each other. Otherwise, the limit doesn't exist. So let's just go back up to those other graphs. Pause the video if you want to write this down. So we would say like, for this function up here, this guy, we could say that this limit exists for as x approaches 5. Because as x approaches 5 from the left, the limit is 2, so that exists. As x approaches 5 from the right, the limit is 2. It exists. And the limit, the left hand and the right hand limit are the same. So therefore, the limit as x approaches 5 exists. So we would say like the limit, I'll just write this in the middle. So we would say like the limit as x approaches 5 of f of x exists. It actually equals 2. But it does exist because it met all the criteria. It had a left-hand limit, check, a right-hand limit, and they were the same. Okay, but this guy, it has a left-hand limit, it has a right-hand limit, but they're not the same. So we would say the limit, if anyone's asking, we would say the limit as x approaches 4 of f of x does not exist. DNE, does not exist. So it doesn't because it's different for the left and right limit. So what would you say if you wanted to say the limit as x approaches 4? You can't. There's two different values. So the limit itself does not exist. Just the left hand and the right hand exist, but not the limit as x approaches 4. So those are the limit rules. So they're pretty straightforward. Okay, and then remember how I mentioned continuous and discontinuous functions? So we have to be able to prove if a function is continuous or not continuous. So we also have rules for that too. Okay, so let's do these. So here's some 3 rules to say if a function is continuous or not continuous. So we say that a function f of x is continuous at a number x equals a if these 3 things are true. First of all, there has to be a y value. So f of a is defined. So that just means wherever you're talking, x equals 2. Then that means there is actually a y value at x equals 2. So f of 2 is defined. Otherwise, obviously, it's not going to be continuous because it doesn't exist in a certain spot. Rule number 2, the limit as x approaches that value, a, of f of x exists. So the left and the right hand limit have to be the same, and then the limit will exist. Okay, that's rule number 2. Rule number 3, the limit as x approaches that number of f of x is actually equal to the y value. So it's saying like this guy must be equal to that guy. So those 3 things have to be true. So let's test it. Let's try it with this graph here. 1, 2, 3, 4, 5. Okay, let's say we're looking at 5 again. It doesn't have to be 5. It could be any number. So let's say we wanted to figure out if this function is continuous. And let's just figure out if it's continuous. Like to me, looks continuous. You don't have to pick up your pencil. You can draw that whole graph. Boom. But let's prove it's continuous using these 3 rules. So first rule, f of a is defined. So that means, so rule number 1, f of 5. What is f of 5 equal to? So let's find the y value at 5. 1, 2, 3, 4. So it's a negative 4. So you have to be good with function notation. If you're like, what the heck is f of 5? Whoops, that's not good. So f of 5 is equal to negative 4. So we've met the first condition. The first rule is f of a is defined. And it is. There is actually a point when x equals 5, there's a y value. Okay, rule number 2. The limit exists. In order for the limit to exist, it has to fulfill the left and right hand rules must exist and they must be the same. So we can see that when we approach the graph from the left and the right, it's going to equal negative 4. So if we're approaching from the left, yep, our limit's going to be negative 4. If we're approaching from the right, if we're approaching 5 from the right, we're also going to end up at negative 4. So the limit as x approaches 5 of f of x is equal to negative 4. Perfect. Rule number 3, that limit has to equal f of a. So boom, they do. So it turns out the limit as x approaches 5 of f of x is in fact equal to f of, oh, I should put f of 5 in all these, I guess, eh? No, not this one. Do I? I don't know. Yeah, that doesn't make sense because I'm talking about the whole function here. I gotcha. Okay, so the limit as x approaches 5 of f of x is equal to f of 5. That's in fact saying that they're both equal to negative 4. So therefore, f of x is continuous. I'm calling it f of x because I don't know what this is a graph of. F of x just means a function, and that's what it is. Okay, so therefore we just proved that this is continuous. So this is just a very small intro to limits. And all we did was prove or figure out what limits are, kind of. And we talked about seeing if a limit exists or not and being able to tell if a function is continuous. You can tell just by looking. I mean, obviously this is continuous and this is not. This is discontinuous or not continuous. Like you can just tell, obviously. But you can also look as it approaches certain values. These guys here too are referred to as piecewise graphs. So like in different pieces. Okay, more on limits next week.